In this lesson, we'll learn about vectors for mechanics. Now, in its simplest form, vectors are basically quantities with both a magnitude and a direction. So we can think about vectors as arrows. So this arrow is telling me to go to 5 units to the right and 2 units up. So we can label this vector as 5 right plus 2 up. Now instead of writing right up or xy, we use a notation called ij notation. In this case, the horizontal axis towards the right is labeled I and the vertical axis is labeled j. In case of navigation, the j axis can be considered to be north and the I axis is considered to be east. The minus I axis is the direction west and minus j is south. So the vector we just saw, 5 right and 2 up, will basically be the vector 5i plus 2j. Now we could have vectors for a lot of stuff. If you remember the different scalar and vector quantities we learned, the vector quantities we learned were displacement, velocity, acceleration, force, and many other ones, momentum included. In case of general mechanics, we only need to use vectors for displacement, velocity, acceleration, and force. We can also use a vector to represent position. In fact, GPS navigation works in such a form. So if I want your exact coordinates, you'll say something like 24.3 north, 15.3 east. So basically your latitude and longitude. This is also a vector positioning. For example, I can consider my house to be the origin. So this is my house. It's my origin, it's the origin. Now with respect to my house, I can find the positions of other people. So I want to say that there is a shop 3 meters to the east and 20 meters to the north of my house. So 3 meter east, so 3i, and 20 meter north is 20j. So the position of that shop is 3i plus 20j relative to me, or from the origin. Now using in vectors, we can use the Suvat equations as well. So the Suvat equations we generally use. So these 5 equations, we might have to use any one of them in vector form. It's basically the same as we usually use when we use that with numbers. Now there is a special link between displacement and position. So if I know the initial position of something, so its position at time 0, we can call that r naught. And if I know its displacement, I can find its final position. This will be r naught plus s. And if we are given 2 position vectors, we can also find the displacement from it. So I might say that there is a shop over here, which is 20i plus 3i plus 20j from my house, which is the origin, and over here at minus 10i plus 10j, there is another house, my friend's house, I can find the displacement from my friend's house to the shop as well. So this vector over here is the displacement vector of my friend's house to the shop. I can find this out by subtracting my friend's position from the shop's position. So basically, if I want to find the displacement of A to B, I'll subtract the position of A from the position of B. Now the Suvet equations are for when there's a constant acceleration. If the acceleration, however, is 0, we can use the formula S equals to Vt. So this is when we have for acceleration equals to 0. When there is no acceleration, we can use the formula S equals to Vt as well. So if I know the displacement, I can find the velocity if I know the time as well. So if I know the displacement and the time, I can find the velocity vector as well. For example, if I am given a displacement, so I can use this reference over here. For my friend's house is at minus 10i plus 10j, and the shop is at 3i plus 20j. Now the displacement from my friend's house to the shop would be the position vector of the shop minus the position vector of my friend's house. So this will be 3i plus 20j minus 10i plus 10j. So we'll have this expression over here. This will come out to be 13i plus 10j. Now if my friend tells me that he needs 2 minutes or 120 seconds to go to the shop from his house, I can find his velocity vector as well. I know that the displacement of the shop from his house is 13i plus 10j meters, and I know that he needs 120 seconds. So from here I can find, you know, that S is equal to Vt. I can make V the subject over here. I'll get S by T. So his velocity vector would be 13i plus 10j divided by 120. So we'll get a velocity. Well, I'll just do it in minutes. I'll find his speed in meters per minute. So I'll get 13 by 2, which is 6.5i plus 5j, and the unit for this will be meters per minute. So this is my friend's velocity vector. Now before we move on to other topics, we'll also have to learn about bearings. So what is a bearing? In vectors, bearing basically means the angle that the vector subtends with north. So if I had a vector 2i plus j, its bearing would be its angle from north or j, and this angle has to be clockwise. So even if I had a vector over here, the bearing would be this angle. This wouldn't be the bearing. This whole clockwise rotation would be. So this is j, this is I. So now if I want to find this angle, I can just use tan theta. So this is theta, the angle I want to find. This is 2i, so this length over here is 2. This is 1j, so this length over here is 1. So I can use tan theta equal to opposite by adjacent. The opposite is 2, the adjacent is 1. From here I can find the value of theta. In this case it would be 63.4 degrees. We also have to remember the vectors of some common directions. The common directions are north, south, east, west, and exactly in between them. So if I begin with north, a vector representing north would be ki. This is north. Sorry, this is kj. Kj represents north. Ki over here represents east. Minus kj represents south. And minus ki represents west. The k I'm writing over here is a constant. So even if I move 5 meters, this will be 5j. If I move 3 meters to the north, it will be 3j. So even if I move a different distance, my vector would be the same, just the value of k will change. Now there are 4 more vectors we have to learn. One of them is northeast. So you go 45 degree from here, or on a 45 degree bearing. You move right and up in the same amounts. So if you go 5 units to the right, you move 5 units up. This vector is represented by ki plus kj. This is northeast. Similarly, this over here is northwest. If you go 5 units right, you go 5 units down as well. This angle over here is 45. Its bearing is 90 plus 45, because this angle over here is 90. This is represented by ki minus kj. This is southeast. We have northwest over here. Northwest is represented by minus ki plus kj. And finally we have southwest over here, which is minus ki minus kj. So this question has all of the concepts that we need. So in the first question, part A, first we'll read the question. So at 10 am, this is the starting point. We are given 2 ships A and B. The position vector of A is given, the position vector of B is given. This is their initial position. We are also given their velocities. And now we have to find their position vector after t hours. So for A, for ship A, the position vector of A after t hours would be its initial position. So this value over here, I plus 3j, plus its displacement. We are given a constant acceleration over here, so we'll have velocity times t. A's velocity vector is 2i minus j, so this will be 2i minus j times t. So we can write down its position vector as I plus 3j plus 2ti minus tj. And if we have something like this, we always separate the I components and the j components. So for the I component, we'll have 2t plus 1 I, and for the j components, we'll have 3 minus tj. And for ship B, in a similar manner, we can find its position vector. Its initial position is 5i minus 2j. Its velocity vector is minus I plus 4j. And we have the time t. So RB over here will be 5i minus 2j minus ti plus 4tj. We'll separate the I and j components again. We'll get 5 minus ti plus 4t minus 2j. Now in part B, we have to find the position of B relative to A. if we are asked a question like this, we'll have to find the displacement of B considering A as the starting point. So in this case, if we are told relative to A will be in the front and B will be here. So this vector. So if I want C relative to D, this vector will start with D and will go to C. So similarly, in this case, we have to find the vector AB, which we know would be the position of B minus the position of A. So the position of B, we know that it's 5 minus Ti plus 4T minus 2J and minus the position vector of A. The position vector of A at time t is 2t plus 1i plus 3 minus tj. So if I subtract them from each other, I'll have 5 minus ti plus 4t minus 2j minus 2t plus 1i minus 3 minus tj. Now I'll separate the I and j components again and then join them together. So if I calculate for the I component, I'll have 5 minus t minus 2t minus 1. So this will be 5 minus t minus 2t minus 1 I, and for the j components, we'll have 4t minus 2 minus 3 minus t. So this will be 4t minus 2 minus 3 plus tj. So over here we'll have 4 minus 3t I plus 5t minus 5j. Now in part C, we have to find out if they collide. So if they collide, at the same time their I coordinate and j coordinate must be the same. So at the same time they must be at the same I coordinate, so the same vertical line or the same line running from north. So if I draw an axis over here, do it in a graph. So this is j, this is I. So we'll have to find the time at which their I values are the same and the time at which their j values are the same. If the time at which their I value is the same and the time at which their j value is the same is equal to each other, they'll meet. Otherwise they won't. So we'll check that over here. If we have the displacement vector, we can also do it by setting this to be 0i plus 0j. So basically the displacement being 0, and then check if the value of t matches. So this is equal to 0 and 5t minus 5 is equal to 0. From here we'll get a value 3t equals to 4, we'll get t equals to 4 by 3. And if I solve this, I'll get 5t equals to 5, I'll get t equals to 1. The values of t do not match. T does not match, so they don't collide. Now in part D of this question, we'll have to find the closest they will come. We have their displacement from each other, which is this vector over here. If I find its magnitude, this will be the distance between them. So if I want to find the minimum distance between them, I'll find their magnitude. We are basically using the Pythagorean theorem over here. Since we know how much it goes to the right and how much it goes to the left, to the up and right, I can find how much it moves in total, which would be the length of the hypotenuse over here. This is 90 degree, so this squared plus this squared will be the magnitude. So over here we can remove the root over by squaring both sides. That will make life easier. I'll have 4 minus 3t square. I can just expand it in this line, get 16 minus 2 times 4 times 3 plus 9t square plus 25t square minus 2 times 5 times 5t. This will be a 3t as well, plus 25. This expression comes out to be 34t square minus 74t plus 41. Now to find the minimum distance, I can either complete the squares from here or differentiate the right side and set it equal to 0. So if I do that, if I differentiate this and set it equal to 0, I'll get 34 times 2, which is 68t minus 74, and we set this equal to 0. We find the value of t to be 74 by 68 hours. So at this time the displacement will be the minimum. I can just put that back into this and get the minimum distance. So 4 minus 3 times 74 by 68 squared plus 5 times 74 by 68 minus 5 whole square. If I calculate this, I'll find the minimum displacement will come out to be 5 root 34 by 34 kilometers. Now in this question we can have a further question of finding the time when it's moving to the northeast. Find t when not moving. We can have when ship B is to the northeast of ship A. Now we know the displacement between them. This is the displacement vector AB. If it's if B is to the northeast of ship A, this will be equal to Ki plus Kj, since northeast is Ki plus Kj. Now we can separately equate the I component and the j component. We'll get 4 minus 3t equal to k and 5t minus 5 equals to k. Now we can just substitute one of them. So I'll substitute k equals to 5t minus 5 from here. So 5 plus 4 equals to 5t plus 3t. The value of this comes out to be 8t equal to 9. T comes out to be 9 by 8 hours. After this, this was for constant velocity. We can also be given the acceleration vector. So if we are given that acceleration is 3i plus 4j meter per second square, and given the initial velocity is 15i minus 10j, we might have to find the final velocity with respect to t. We can just use v equals to u plus at over here, or if they want the displacement, we can just use ut plus half at square. So if they want the final velocity, we'll use 15i minus 10j plus 3i plus 4j times t, and then calculate v, which would be 15 plus 3ti plus 4t minus 10j. Furthermore, we might also be given the force vector. So we might be given that the force is 6I plus 8J Newton, and we are given the mass is 2 kg. From here we can find the acceleration vector, because F equals to mass times acceleration. 6I plus 8J will be 2 into A. From here we could get our acceleration of 3I plus 4J again. This will be 6I plus 8J divided by 2, 3I plus 4J. Or we might be given the acceleration vector and we might be asked to find the force vector. And especially in the case of force, we might be told that forces or a particle is at equilibrium. In that case, the resultant force vector will be 0I plus 0J, since there will be no acceleration when it's at equilibrium. And this covers